Good evening. It looks like it's 7:30, and we're going to go ahead and get started with the Wednesday night midterm review. I'm going to be doing a couple of different things here. I'm going to review a couple of PowerPoint slides here and there, and I'm also going to go through the study guide a little bit. So in fact, I'm going to start out sharing that study guide here. That'll pop up in your window in just a moment. The purpose of this review session is to go through the topics that I think are important to spend time on, and so hopefully you'll find this useful. If you need to ask questions, want to ask questions, there's two ways you can do it. There is there's a chat area. It should be available here. You can also text me at 414-899-8269 if for some reason your chat isn't working. And so feel free to ask questions or clarifications. And unfortunately, I can't hear you. That's not the way we're set up here tonight, but that should be okay. So what I'm going to do is go over a couple of things here. First, talk about what we're going to do. We looked at this study guide. You saw it online, and we briefly went over it in class. You should be familiar with the overall software development process and the software management process, and what those component activities are. You'll also want to be able to sketch out the 4+1 elements of the 4+1 view of architecture that we've talked about, which includes the use cases in the middle, and then logical development, deployment, and process view. The reason I put that up at the beginning of the year is for us to sort of orient ourselves around the different ways we're going to look at software engineering, rather than just sort of saying it's a big ball of wax. We think of software engineering as a variety of activities, but pervading all of this is the issue of modeling. And I may be a little bit of a traditionalist here, but I think it's important to be able to sketch out comprehensible designs, not comprehensive, but comprehensible designs of a large system. And in particular, when we're looking at either adding features or building whole new systems, the ability to logically catalog all of the different functional requirements is really important, and that's why we start with the use case diagram. So use cases, use cases are a way of describing how the system responds to events that are generated by actors outside of the system, beyond the system boundary. So you'll want to know use cases, actors, and system boundaries, and then their relationships. In other words, if an actor is going to interact with a use case, there'll be a relationship between the two. You should have a good understanding, not only from this class, but from prior classes, of the difference between a class and an object, and why we have class diagrams and object diagrams. Object diagrams allow us to understand the structure of a system by thinking about what objects exist, how they're interacting with each other, and what their relationships are to support the responses to events outside the system. We then generalize those objects into classes. In other words, we say, this object belongs to a certain class of objects, and we then define those objects as part of our exploration of the domain. So we create a domain model with our class diagram. We think about the associations between those types of objects. We then are able to think through different scenarios by sketching out communication diagrams or interaction diagrams and understanding what objects are participating in each of the scenarios. And I know that sounds a little bit maybe formal or complicated, but it's really the way we think about large-scale systems and thinking about all the different interactions. You should be familiar with the notion of iterative development and why we have iterations. Agile development is one form of iterative development where we reduce risk in the system by doing the riskiest parts of the system early on, those things that are most important, that capture the key abstractions, that capture the key mechanisms, and we do that early on. The book has a very good description of requirements modeling. And one of the things I found in my career, at least, is that when you do requirements well, the rest of the system falls out pretty easily. When you do the requirements badly, you struggle throughout the development effort. And I suppose that's like a lot of other things. So the use case model is really a way of modeling functional requirements in the system. And so we identify actors, and we talked about mechanisms for doing that. So you'll want to be able to identify those, and then the thinking about what elements are within that use case model, and being able to sketch out scenarios, because what we're going to find is that as we are identifying use cases and creating descriptions of them, if you'll recall our monopoly example, that when we're looking at descriptions of them, we really go through different scenarios. That's really how we think about this in many cases, is we say, well, let's imagine the scenario for, say, an ATM where Tom goes up and asks for $60 and he's got $80 in his account, and it says, sure, here's your $60 in 320s, and then prints a receipt and he walks off. And then we say, well, what happens if he doesn't have enough money? So now we explore what happens in an exception, and we try and anticipate alternate flows. We say, well, if he doesn't have enough money, let's not just create an error and stop. Let's anticipate it and say, well, an alternative would be that he doesn't have enough money, and we're going to say, you know, it exceeds your current balance. Would you like to try another amount? And perhaps even offer the balance so they're not just stabbing away at it. So we try to avoid true exceptions, which is when we've run into an error condition that we can't handle. An alternative flow is where it's not what we're expecting, but we know how to handle it when it occurs. It's a subtle distinction, but it allows us to recover from that error, back up to a known state, and continue. So as we look at those requirements, we're looking for functional and non-functional requirements. Remember that functional requirements is how the system responds versus non-functional requirements, which is what that response looks like. In other words, how it behaves. So if we say that the system gives Tom $20 back, we might qualify it with how quickly it does it, or how reliably it does it, or how many people can get $20 back at the same time. Those would be non-functional requirements. So you're thinking about, from a logical perspective, from a functional requirement is what value is being delivered versus how it's being delivered. So if I say that something measures the temperature and stores the temperature, that's a functional requirement. If I say that it stores it as an integer or as a floating point, that's not really changing the value of the proposition. It's simply telling us how we intend to implement it. So as we go through that, we're also creating our domain model. And remember that analysis is a process of identifying what things we know to be in the system. And by doing this, we have, we're basically creating a catalog of all of the interesting entities in our domain. They're not our design model. In other words, we're not thinking about how we're going to build it. We're thinking about what things exist in that domain, how they are expected to behave, or what information they're expected to maintain. And then we're going to create a design that implements or automates as much of that domain model as is appropriate within our system boundary. And one of the things I did early on was introduce testing. So I sort of dragged that up in the order in the book. And the reason I did it is I wanted a lot more focus on the notion of test-driven development. By that, I mean, as we create our requirements, we're constantly thinking about how we can test this. And it's not so much testing from an implementation perspective, of course that's important, but we're also saying, do we in fact meet the requirement? Because at a high level, especially as we do system tests, our tests are intended to determine whether we're in fact meeting those requirements or not. So if we say that if Tom goes up to the ATM and asks for $60, how do we intend to test that requirement? And so if the requirement is that following the distribution of the $60, that his account should now have $20 in it, that, in other words, a withdrawal has occurred, we know how to test that. And here's an important thing here. We want to make sure we understand the difference between test plans and test cases. So test plans are how I'm going to go about testing something. And we talked about this in class for a minute, but I just thought I'd bring it up again. And that is, test plans describe timing, who's involved, what resources are required, what the purpose of the test is, and then it also includes a set of test cases. The test cases are the ones that include what the input value is, or the input event, what the expected output is, and what the observed output is. And that observed output may be a return value from a method, or it could be a side effect, such as sending a message to another object or issuing a message to an outside actor of some sort. So test plans involve test cases. Test cases specifically test for input to output mappings. Test plans tell us how we're going to organize those to achieve a particular result. And we looked at a couple of different aspects of testing. Black box testing was less concerned about what was happening inside and more concerned with testing particular boundary values. Saying, for example, if I've contracted to have my ATM software built, I'm going to go through all of the use cases that are important to me as an owner of an ATM system. And so we talked about acceptance and system level tests. An acceptance test is when a customer or client says, I'm going to run a series of tests, and based on the outcome of those, I will either decide that the system is complete or not. And so that's typically considered black box testing, because we're not really concerned with the inside as much as we are concerned with the output, the input to output mappings. White box testing is typically performed at a lower level and by developers or test teams or QA teams. And the purpose of this is to really stress that particular, in our case, object, since we're in an object modeling environment. Excuse me. We're in an object modeling environment. So we have several things we have to do. One is we have to make sure that we test all of the methods in a class. We want to be thorough. We don't just test the ones we kind of like. But not only do we have to test the methods, we have to test it based on any inputs that come along with those methods, in other words, the parameters. And based on that, we have to make sure that we hit all of the statements that should be executed within each method. And we do that by making sure that we take each branch in the system. And so that's why we came up with this notion of the flow graph. We said, well, within a method, we have to make sure that we hit all of the different conditionals. And we wound up doing some calculations with our basis path to create a cyclomatic number that said that the cyclomatic number is the number of edges minus the number of nodes plus 2. And we didn't go into the math, the graph theory math, as to why that works out. But for a given method, that's the special case of a larger graph. And so edges minus nodes plus 2 gives us the number of unique paths through that method. However, if you have a compound conditional, you have to take into account the fact that there are multiple branches within that technically. In other words, if you have A and B, some conditional and some other conditional, you have to really consider that that's two different conditionals that have multiple branches between them. And we saw the example. So you'll probably want to go back and take a quick look at that. The reason that I push on this, that I put so much emphasis on this, is I want you to keep in mind as an engineer how complicated your methods are getting when you supply a large number of parameters, because each of those parameters are potentially inputs to different conditional values, or they're being passed on to other methods outside. If we have a situation where we have a number of different branches, our cyclomatic number is going to go up, our complexity goes up, our risk goes up. It's that simple. And so within methods, we try to reduce the number of branches possible, therefore the cyclomatic number. Now, the reason we want to do that is not only do we have complexity in the branches, but anytime we send a message off board, in other words, out of the object to another object, we rely on that connection. So that if that external object changes, then I change, or if I change and I have to change the external object, I now have introduced more complexity. And that's why we have the notion of cohesion and coupling. Now, it's not actually written down in the study guide, but it is in your notes. I mean, in your slides too. Cohesion and coupling give us direct measures of complexity based on our dependencies on other objects. If I have a high degree of coupling, that means that an object requires the services of yet other objects in order to complete its tasks in some fashion, or that other objects are expecting messages from it. The greater the coupling, the more change is going to affect a system, which is going to increase the risk whenever I make changes. Cohesion is a measure of how related the objects within a subsystem are, or how related the objects and the data and methods are within an object. In other words, how relevant are they to each other? So you want good cohesion and low coupling. In other words, you want high cohesion, they're all relevant. Low coupling, I don't need many things off board. That's the optimal situation. But what happens? If I have really great cohesion, the objects get bigger and bigger, complexity goes up. That's bad, so I break it into smaller pieces. So there's always this dynamic tension between size and breaking it into smaller pieces, but the smaller the pieces I break it into, the more complex the system gets. So we always reach sort of a happy medium there. And then finally, we were talking about, we said, well, as we get into design and we start talking about the design of objects to meet the needs of actually building the objects that will participate in our responses to events in the system, we started to ask about how we might take advantage of prior solutions to similar problems. So a pattern is basically a generalization of solutions to a particular problem, distinguished by the particular constraints. So we say that a pattern is a solution to a problem in a context. In other words, the solution itself, the one you come up with, is where I take a pattern, apply the constraints or the variables to it, and say, okay, here's how I'm going to assign the roles and the relationships that I have in the pattern to my actual needs in this specific design case. So we saw the example with the model view controller, where we said, well, in the case of the model, in the case of the thermometer, we said the actual model was the current temperature. And we said that when the actual measuring device, whether it's a bimetallic strip or some solid state device, detects a change in temperature, it generates an event to the controller, which interprets it, changes the model. And then we said, well, we have ways of actually seeing that temperature. For example, we might have a dial or a gauge or a digital display. Those were simple ways of viewing that model, a way of transmitting it from inside the system to outside, across the boundary. There we assigned different roles to different objects. The temperature was the model. The controller was the one responsible for interpreting the event coming in from the actual temperature sensor. And the digital gauge was the view. And so we did the same thing when we said, well, in the case of the command pattern, we saw that relatively nifty tool where we said that the invoker was the actual tool framework. The commands were either cut or copy commands. And the target was in this case, the block of text. And so we assigned those roles to each of those and said, well, if we have a command, this is how it works. The invoker creates an instance of the command, tells it to execute on the assigned subject, and then when the command is done, I can put it on a stack of commands. And so we know that we had command patterns. We saw the interface pattern with the compiler. That's a handy one to know. And that one is valuable because what it does is it says this single object is going to act as an interface to the rest of the system. And in this case, the compiler supported the only interface to the compiler, which was, hey, compile this source. It delegated all the responsibility of lexical analysis and graphical analysis, syntactic and semantic analysis to other components within the system. The code generation, the code optimization were all done by individual components behind that interface, though. We saw the publish subscribe pattern, which we also call the observer pattern. Those names are interchangeable. Oh, also, the interface pattern is also called the facade pattern. So interface and facade are really one and the same. And then finally, we had the publish subscribe or observer pattern, which solved a very common problem, which is when the state of an object changes, there are other objects that want to know about it, but they don't want to have to keep polling the target object. And you don't want to have to build it in a hardwired fashion into the object that's being observed or the subject. So we came up with this very nifty, loosely coupled and loosely typed interface that said, well, I'll just keep a collection of any old object that wants to know. As long as it responds to the message notify, off it goes. And in fact, it's used directly in the model view controller pattern. So the model view controller pattern, which you'll want to know, is in fact employs the observer pattern in that whenever the model changes, it tells any of the views that are observers of that model to update themselves. And then finally, we also had the memento pattern, which is going to be sort of the bridge into our discussion of persistency after we get back from break. And the memento pattern is a way of remembering other objects, remembering the state of an object so that it can be reconstituted. In other words, it can be built back up again from that memento. And we're going to use that as the basis for our persistency approach later on, whether we're storing it in a file, a flat file, or a Mongo database, or a relational database, or what have you. So in addition to these 4 patterns right here, you'll also want the let's see, I was going to put a little note on here. No, I can't do that here. Never mind. You'll want to know the model view controller. So as a couple of quick notes here, in addition to the design stuff that we talked about, we'll want to know about cohesion and coupling, which we sort of left out of this note here. But it is in our slides, and it's also in the reading for the book. So I'm just going to scoot over to the PowerPoint for a second here. I'm going to stop sharing this one. And I'm going to go over and grab a little PowerPoint here. Let's see. Where is it? Remember the first slide, basically, on the first day, good old Brad Cox said, you know, software is funny because it's too thick to drink, too thin to plow. It's this weird difference between a service, the manifestation of a service, and a product. And so we have a lot of unique challenges in software. And so in the course of 361, we're looking at software engineering, which is not only the design and development of software, which is what we often think about, but it's really the specifications that precede it, analyzing them, understanding how the system is to respond to events, and who's going to participate in it, and to be able to trace those requirements and understand whether we've met them satisfactorily. Actually develop the software products that do that, designing them in a way that they can be tested, therefore demonstrably accurate. We need to be able to manage this process so that we can produce the software within time and budget, all the while managing the risk involved. As risk goes up, time tends to extend, budgets tend to go up. In other words, cost tends to go up. So we're constantly monitoring our project to ensure that we're within time and within budget so that we can make small adjustments during the course of the project so that we don't wind up wildly off course. And that's why we use agile development techniques or iterative development techniques in order to reduce that risk by constantly assessing where we are in our, as we seek our goal of meeting the specifications in a demonstrably accurate fashion. And we do that by designing and developing software that can be tested, that in fact meets those specifications, is relatively low risk and low cost. And we can do that by using patterns to solve the problem, so we're not solving the problem all over again. We do that by understanding what tasks we have to do, by breaking the system into smaller, manageable parts without creating an overly complex system. So in the first half of this course, what we've done is we've looked at how we analyze systems, how we can design objects within them, how we can then use patterns to help us do that more quickly, how we can test the system. And now we're going to look at some more detailed design activities, such as persistency and state and threads and some other architectural issues. And then we're going to go into the process of managing the process of building software as well as version and configuration management. So what we've got here is relatively straightforward at the midterm. I think if you've come to lecture, if you've done the quizzes, you should be able to get to all of the quiz answers. If you're not seeing it in your case, text me and I'll make sure that you can. But I think you should be able to see all of them. And then tomorrow There is going to be a little bit of reading, some requirements. You can take 5 minutes to do that. There's 25 multiple choice questions. Some are small and fast. Others will require that you do a little bit of thinking. There'll be plenty of time to do it. And we'll try and get those graded right away. Well, if there aren't any questions, that's what I think you should probably know for tomorrow. Hopefully, this has all been covered pretty well in lecture. I've tried to emphasize the points that I think are important from the book, although I'm expecting you to have read all of those different sections. And then the labs were designed to reinforce that. I don't think we have anything on the test that's relative to the labs. So we'll see you tomorrow at 10 o'clock. Bring a pencil and do your best. Get a good sleep tonight. Thanks very much for coming.